All right, good afternoon. Just going back to where we left off, okay, working with asymptotes and again, along with vertical asymptotes, okay, we had horizontal and slant asymptotes and just kind of giving the rundown, okay, for these other asymptotes. Again, if you have a ratio of polynomial expressions, okay, where we have n to be the degree of the numerator, m to be the degree of the denominator, we have that if the numerator degree is less than what is in the denominator, again, there's going to be a horizontal asymptote, y is equal to 0. And again, y is equal to 0 is going to be the x-axis. And if it turns out that the degree in the numerator is the same as what is in the denominator, we're going to have a non-negligible horizontal asymptote, and that is going to be where y is equal to the ratio of the leading coefficients, which will reduce to a constant. And again, if we have the numerator degree to be greater than the degree of the denominator by 1, okay, then there's going to be a slant asymptote. And if the difference is by more than 1, okay, you're not going to have any horizontal or slant asymptote to exist. Okay, now just looking at some of the items that we have and to give you a bit of a visual. So just kind of going back, okay, say if you're looking at determining, okay, the domain and the asymptotes. I'm sort of going to repeat this one. Okay, so we have for the domain and the asymptotes. Okay, so we have, in the case of our function r of x, again, we have equal to, once again, we have x cubed plus 3x squared plus 4x plus 1. And again, we have all over x squared plus 1. And just to sort of restate, okay, now, again, for the rational expression in the form of a fraction to be defined, again, the denominator cannot be equal to 0. And just like what we had last time, okay, so I cannot factor a sum of squares. Okay, but if I isolate x squared, so I have the x squared cannot be negative 1 in order for x squared plus 1 to not be 0. And again, if I take like the fundamentals from the square root property of equality, so if I go from x squared to x, I have the constant negative 1, where I'll be taking its plus and minus square root values. And once again, we have for x, any exclusions from the domain are not going to be from the real number system. Okay, so in this particular case, right, so we have no real values excluded. So that means x can be any real value. It could be 0, it could be any positive real number, as well as any negative real value, because anything that's excluded is not even a real number. And so for again, we have for the domain, since nothing is left out from the real number system, we can say that for the domain, we have the set of all real numbers and an interval notation. Okay, we have parentheses around negative and positive infinity. Okay, and since there are no real values excluded, okay, there are no restricted values from the real number system, so that means that there will be no vertical asymptote. and for what we have in terms of the appearance of any asymptote period. And once again, this will come down to the degree comparison. Okay, so we have both polynomials are in descending degree order. And now for the numerator, okay, the n value is going to be equal to 3 since x cubed is the highest order term. And then we have in the denominator, okay, higher order term, we have x to the second, so we have the m is equal to 2. And so we have here n at 3, m at 2, and so we have 3 is greater than 2, and the difference is 1. And again, we're going to have a slant asymptote. So I have n is greater than m by 1. Okay. And just to restate, we have a slant asymptote. And this is going to be a straight line. Okay. And so we have and again, y is going to be equal to the quotient result of taking x squared plus 1 into this 4-term polynomial. Okay, so I'm just going to repeat here. And again, I like using synthetic division, but since the divisor is not a first degree in x, okay, we have second degree instead. Okay, so I'm looking at taking polynomial division once again by taking long division. Okay, so I'm kind of putting this problem up once again, and just again, so you have both sets of terms are in descending degree order. So you have x squared and x cubed. We'll go x times, and distributing x over x squared plus 1. So x times x squared is x cubed. And we have x times 1 becomes x. Now x is a first order, and that is going to be placed not underneath the 3x squared, but underneath the 4x. Because you want the degrees to match in order for there to be like terms joined together. So we have in the setup. So if I look at subtracting once again, so we're going to have x cubes are going to go out, and 3x squared, there was nothing situated underneath it. So I'm just going to bring this down. Now we have 4x taking away x. So this is going to be at 3x. And then we have bringing down the plus 1, which has not been touched yet. And we have for the next go round, okay, going from x squared into x cubed to x squared into 3x squared. So we have going in 3 times. 3 over x squared becomes 3x squared. And we have 3 over 1 is going to be 3. And once again, taking the difference. Okay, so for this time, okay, 3x is not touched, and this will be brought down. And then we have 1 minus 3. It's going to be at negative 2. And I cannot take x squared into 3x, okay, and so the remainder here will be at 3x minus 2. But for looking at the determination of the slant asymptote, okay, we're going to be looking at just the quotient result. So in this particular case, right, we're going to have for the slant asymptote, we're going to have that y is equal to x plus 3. So just kind of looking at this once again. So again, x squared plus 1 has no real value exclusion. So x could be anything. So the domain is all real numbers. And since there were no real values excluded, again, there was no vertical asymptote. And in terms of any asymptotes, now, I've been asked this before about whether you can have both horizontal and slant asymptotes. And the answer to that is no. Okay, so it's going to be one or the other if there's to be any asymptote outside the vertical asymptote. And just looking at what we have from a visual perspective and see if I can get this to appear. Yes. Okay, so we have just for this illustration, and again, R of x is just a functional notation for what we say is going to be y. Okay, so just to kind of give you a bird's eye view. Okay, so for the graph I have in red, that is your R of x. Okay, so you have, okay, so this, in a sense, I guess you say, it looks almost like a bell curve that's kind of turned on its sides instead of kind of standing upright. And then for the blue line, that is going to be the asymptote. That is slanted. Okay, if you notice, we have running tangent in the lower left and the upper right hand sections. But notice for the activity that we have in between, notice that there is an intersection. And I just wanted to kind of bring this up, that R of x not always, but in most cases, I would say probably not, but R of x can touch or intersect it can intersect horizontal asymptotes and slant asymptotes. But I just wanted to, and I said this the other day, okay, R of x never touches vertical asymptotes. So I just wanted to reaffirm that. Okay, so R of x, okay, vertical asymptotes are off limits, but in terms of horizontal and slant asymptotes, given the nature of the function itself, it can potentially touch, even intersect horizontal and slant asymptotes. Now, we have as a case involving the determination of domain. Okay, now we have just for this next item, and we have for R of x. Okay, so we have equal to 2x squared minus 18. And we have all over x squared plus 5x plus 6. And again, looking for the domain. Okay, you're looking at finding out the restricted values before any reduction is performed. Okay, so we have the denominator, x squared plus 5x plus 6, okay, which cannot be equal to 0. And taking what we have in the case of the factored form, okay, so you have the quantity of x plus 3, and the quantity of x plus 2, okay, so the product cannot be 0, and so that means that neither of these factors can be equal to 0. Okay, so we have x plus 3 cannot be 0, as well as x plus 2 cannot be 0. So we have left out from the domain, we have negative 3, as well as negative 2. All right. So we have, in the case of the domain of this rational function, okay, so there are two excluded values with negative 3 and negative 2. So we have at the lower end, we have those values of x that will be less than negative 3. So negative 3 is going to be bypassed. And then we have going past negative 3, approaching but not including negative 2. And finally, we have bypassing negative 2. So we have for the rest of the set, it'll be those values of x, okay, which will be greater than negative 2. Right. So that is the domain. And again, you're looking for the restricted values before any kind of reduction is performed. Okay. So where the, at least where the vertical asymptote or asymptotes will be determined. Okay. So we have a 2x squared minus 18. So here, greatest common factor is going to be at 2. And I have times the quantity of x squared minus 9. And for x squared plus 5x plus 6, okay, so we'll have the quantity of x plus 2 times that of x plus 3. And still I have the difference of squares with x squared minus 9. So factoring furthermore, okay, so I have the quantity of x plus 3 times that of x minus 3. Okay, so we got in the setup. Okay, if you notice, okay, we now have like factors with x plus 3, so I can perform reduction. Okay, so x plus 3 cancels, and it's going to cancel completely, so x plus 3 is no longer in the denominator. So this is going to signal that there will be a whole at x is equal to negative 3 and for the reduced form, so we have 2 times the quantity of x minus 3. Okay, we have all over x plus 2. And again, x plus 2 stays. And since that factor stays, that means that we're going to have a vertical asymptote. And this will be at x is equal to negative 2. And just looking at what we have regarding the degree comparison. Okay, so we have in this setup, okay, so you have a vertical asymptote at x is equal to negative 2. And for the degree comparison, okay, so we have in the numerator, okay, we have from the square in 2x squared, okay, we have the degree to be at 2. And from the denominator, okay, we have the term at x squared, so we have the m is equal to 2. And we have from the start now, in terms of how n and m are going to compare, okay, these are identical. So we have that n is equal to m. So along with the vertical asymptote at x is equal to negative 2, we're going to have a horizontal asymptote. And this is going to be a constant that results from taking the ratio of the highest order terms from the numerator and denominator. Okay, so you have 2x squared over x squared. And so this is going to reduce to y is equal to 2. Okay, so we have two asymptotes, one vertical at x equal to negative 2, one horizontal at y is equal to 2. Let's see. Okay, so just with what we have here, okay, so we have in the graph, okay, so you have y is equal to 2x squared minus 18. And again, we have all over x squared plus 5x plus 6. Okay, so just looking at, okay, so for the sections in blue, okay, so we have in reference to r of x equal to 2x squared minus 18 all over x squared plus 5x plus 6. And again, just for the items here, so for that which I have kind of like with this purple line, again, this will be the horizontal asymptote y is equal to 2, and the line in green running vertically, again, we have x equal to -2. And if you notice this little open circle here, again, this is signifying that we have a hole at x is equal to -2. Made that -3. Okay. All right. So we have in this particular case, right? So you have a hole at x equal to -3. Okay. Now, in looking at what we have in the mix, and we have with the next item. Okay, and so we've got on page 318, and we have for this particular group of problems. Okay, so we have in 59, okay, so you have a function f of x. Okay, we have is equal to 4x minus 9. And we have all over x squared minus 9. Okay, now looking at what we have for the domain. Okay, so again, you're looking for the restricted values before any kind of reduction is performed. So again, we have x squared minus 9 cannot be 0. Okay, so looking at each factor. Okay, so we're going to have the restricted values to be additive inverses. Okay, so we have x cannot be -3 or +3. And so we're going to have for the domain. Okay, we have those values of x less than -3, but not including -3. Have likewise between negative and +3, and again not including either of those two values. And then for the rest of the domain, we have those values of x which will be greater than 3. And in the case of what we have regarding the vertical asymptotes, okay, so we have here got 4x minus 9 all over, and again we have the quantity of x plus 3 times the quantity of x minus 3. Okay, if you notice, we don't have any common factors between the numerator and denominator, so there'll be no cancellations. Okay, so both x plus 3 and x minus 3 are going to remain. And because of this, okay, we're going to have not one but two vertical asymptotes. So both of these exclusions from the domain are going to be converted to asymptotes. Okay, so we have x equal to -3 as well as x is equal to 3. And for what we have in terms of any other kind of asymptote, so you have f of x equal to 4x minus 9 all over x squared minus 9. And looking at what we have for the comparison of the degrees, okay, so you have just with 4x, same as 4x, 4 times x to the first. So you have that n is equal to 1. And from the denominator, the higher order term, we have x squared. So we have that m is equal to 2. And in terms of how n and m are going to relate, we have the n is less than m. So in addition to the two vertical asymptotes, we're going to have a horizontal asymptote, and that is going to be y is equal to 0. And so for what we have in the settings, or among the settings, okay, so we have okay. So we got the illustration of 4x minus 9 over x squared minus 9. Okay. Okay, now I'm just going to mention, okay, so for this line, or this array, okay, so you have a vertical line, we have, again, the vertical asymptote, okay, which we have at x equal to -3. And again, we have with the other vertical asymptote, this purple line here, I know it's all kind of squeezed in together. And then for the three sections here, those will be in reference to r of x is equal to 4x minus 9 all over x squared minus 9. And this one, okay, so you're going to have also in the mix, you're just going to show this, show up a little bit better. And we have just in the case of the extension, okay, so you're going to have a horizontal asymptote, again, which we're going to have at y is equal to 0. Okay, again, the vertical asymptotes are off limits, but again, given just the right conditions. And if you notice, okay, to the extreme left and also to the extreme right, okay, you have the graph of r of x to run tangent to the horizontal asymptote. But if you notice in this middle section, there is an intersection. So the function can come into contact with the horizontal or slant asymptotes, but never the vertical asymptotes. So this is another case of what is described. All right, now for the next item, okay, and we have with number 60, and we have similar kind of function, and in this one, so you have for 60, okay, so you have f of x. Okay, you have is equal to 5x minus 8. Oops. So again, we have f of x is equal to 5x minus 8. And we have all over x squared minus 4. And looking for the domain. Okay, so again, the denominator cannot be 0 in value. And we have with this difference of squares, okay, looking at the factors, and again, neither one of which can be equal to 0. And we're going to have for the exclusions from the domain, we have a bit of partial history to repeat in the sense that the exclusions are going to be additive inverses, where this time we have that x cannot be negative or positive 2. And so we're going to have for the domain, we have those values of x that will be less than -2. And then we'll have those values of x, okay, between but not including negative or positive 2. And finally, we have those values of x to be greater than 2. And looking at what we're going to have in the asymptotes. So again, we have 5x minus 8 over x squared minus 4. And this is going to be another case, again, of where the additive inverse exclusions from the domain will end up as vertical asymptotes. Okay, because once we look at factoring, there's no expression to cancel out that is common to both the numerator and denominator. Okay, and so we have both x plus 2 and x minus 2 remain. So we have our vertical asymptotes will be x equal to negative 2 as well as positive 2. And looking at, again, what we have regarding the degree comparisons. Okay, so you have 5x minus 8. And we have all over x squared minus 4. Okay, and the leading term in the numerator, again, we have 5x, or 5x to the first. Okay, so we have n is equal to 1. And from the denominator, okay, we have m is equal to 2. So we have that n is less than m. And if the numerator degree is less than what we have in the denominator, okay, so we have a horizontal asymptote, once again, where y is equal to 0. Okay. So looking at what we have here. And complete this as well. Okay, so you have, so you got, again, you have 3 sections. Okay, and these blue curves, okay, are in reference to our rational function. And again, we have for the vertical lines in red, we have x equal to negative 2 and x equal to 2. And then we have also included, okay, so there was a horizontal asymptote, y is equal to 0. And again, so for y is equal to 0, again, that is going to be the x-axis. And once again, we have a bit of history to repeat. Okay, you have to the extreme left and right, okay, the graph of the function runs tangent to the horizontal asymptote. But if you notice in the middle section, you have another location of intersection. All right. Now, and looking at what we have in the case of number 70, okay, and this one, in comparison, okay, at least structure-wise, gives me simpler, I think, than what we have dealt with so far. And now we have in 70, you have just a ratio of linear terms. In this case, you have a function g of x is equal to x minus 3. We have all over x minus 1. And okay, so we have for this ratio. Now we're going to have g of x is already in simplest form. So we're going to have the exclusion from the domain, okay, to be recycled essentially and define the vertical asymptote. Okay, so we have initiating. Okay, so you have with this rational function, again, the denominator cannot be equal to 0. There's only one exclusion, and that is going to be 0. And we have in the case of the domain. So we have those values of x, okay, they'll be less than 1. Now, so we have those values of x which will be greater than 1. And again, since x minus 1 is going to remain, okay, since g of x is already in simplest form, okay, we have the restricted value is going to be the vertical asymptote. So we have x is equal to 1. And for what we have in the case of, once again, the degree comparison, okay, so you have g of x equal to x minus 3 all over x minus 1. Okay, and again, both of the higher order terms are going to be a first degree. So you have n is equal to 1 and m is equal to 1. So you have that n is equal to m. So if n is less than m or n is equal to m, there's going to be a horizontal asymptote. But now, with the degrees being the same, okay, the horizontal asymptote is one where y is set to a non-zero constant. Okay, and this will be attained by taking the ratio of the highest order terms. Okay, so you have x over x. So the horizontal asymptote is going to reduce to y is equal to 1. Okay, so we have two asymptotes, one horizontal and the other vertical, okay, where we have respectively y equal to 1 and x equal to 1. And so just looking at what we have here. Okay, so you have y, or g of x equal to x minus 3 over x minus 1. So you have these sections, these curves, okay, separated, okay, and we have, and again, just for the vertical line, this is going to be in reference to x is equal to 1 and the line, the asymptote running horizontally. Again, this will be in reference to what we have with y is equal to 1. Okay, and again, we have both of these sections are going to run at the extremes in tangent fashion to both of these asymptotes. All right. And now, for what we have in the case, so 70 was a relatively a quick follow-up, okay, to what we have had from the previous problems, and we have now just looking at similar type of scenario, and we have in the case of number 72, for 72, okay, so you have a function h of x, and that is equal to 2x minus 4. And we have all over x plus 3. And looking at what we have, okay, for the domain. Okay, so we have the x plus 3. cannot be 0, so we have that x cannot be equal to negative 3. Okay. So we have, for the domain, we have those values of x. Okay, that will be less than negative 3. Along with those values of x, which will be greater than negative 3. And once again, we have that h of x is already in simplest form. Now the numerator could factor out to 2 times the quantity of x minus 2, but there's not going to be any cancellation of terms between the numerator and denominator. Okay. And so our restricted value is going to be the vertical asymptote. And in the case of any other asymptotes, okay, so again, this comes down to degree comparisons. And once again, we have 2x, or 2x to the first is the higher degree term in the numerator. And in the denominator, we have x, or x to the first. So we have that n is equal to 1, and that m is equal to 1. And you have, again, so you have n and m are going to have the same value. Okay. And for what we have in the case of the asymptote, this is going to be, once again, a horizontal asymptote. And we have y is equal to a constant, and this will be taking the ratio of the higher order terms in the numerator and denominator. So from the numerator, I have 2x, and from the denominator, I have x, and 2x divided by x goes to 2. So again, the asymptotes, we have the vertical asymptote x equal to negative 3, and the horizontal asymptote, okay, we'll have that y is equal to 2. Okay, and so for what we're going to have in the overall picture, okay, so we got the rational function, and let me, there we go. Okay, so we have in the overall picture, okay, so you have y, or what we have for h of x, you have x minus 3 over x minus 1. Okay, so I have these curves in the upper left and the lower right hand sections, and again we have y is equal to 1, the horizontal asymptote, and we have x equal to 1, which is the vertical asymptote, and again the curves representing the rational function, once again they're going to run tangent at the extreme ends with respect to the vertical and the horizontal asymptotes. Alright, now for what we have for number 86 and number 90. Now these will be different kinds of functions. Okay, and so for what we have here, so what did I do? 2x minus 4 over x plus 2. Okay, wrong. Wrong asymptote. Okay, so you're going to have the curves laid out as such. So again, we have the vertical asymptote. Now y is equal to 2. And the vertical asymptote at x equal to negative 3. Okay. Yeah, methinks I lost my place. Okay, so you got y is equal to 2, x equal to negative 3. And again, just for the graphs here, we have in reference to y is equal to h of x is equal to 2x minus 4 over x plus 3. All right. Now, for what we have in the case of number 86, okay, and so we have a function u of x, and that is equal to negative 3x squared all over x squared plus 1. Again, if we're looking for the domain and the asymptotes. Now there's going to be a bit of history to repeat. If you notice we had that x squared plus 1 to be in the denominator. Again, you can factor a difference of squares, but you cannot factor in integer coefficients a sum of squares. So again, if I isolate x squared, so I have x squared cannot be negative 1. So that means that x cannot be plus or minus the square root of negative 1. So x cannot be plus or minus I. So again, there are no real values excluded. Okay. So once again, we have for the domain, so we have the set of all real numbers. Again, we have an interval notation case. So you have parentheses around negative and positive infinity. And again, since there are no real values excluded, there's going to be no vertical asymptote. And to see if there's any kind of asymptote to appear, so looking at the degrees of the numerator and denominator. So you have from the numerator, okay, so you have n is equal to 2. And from the denominator, okay, have that m is equal to 2. Now the values are the same. So you have n is equal to m. And again, if the degrees are the same, okay, there'll be a horizontal asymptote. And we have y to be equal to, and so here we have with the ratio of the higher or highest order terms. Okay, we have negative 3x squared, and from the denominator I have x squared. And so we're going to have y is equal to negative 3. So for this function, there's only one asymptote, and that is going to be the horizontal asymptote. Y is equal to negative 3. And so looking at what we have here. Okay, so we have with our rational function, in a sense, this looks almost like a bell curve situated below the x-axis. Okay, and there's only one corresponding asymptote, and that's going to be the horizontal asymptote, which we have at y is equal to negative 3. So you have that line in red, and notice we have at the extremes. Okay, so we have the rational function will be running tangent to that particular horizontal line. Okay, so there's only one asymptote, and again, that is going to be at y is equal to negative 3. All right, now, in the case of our other kind of function, and we have with number 90, And we have with number 90. Okay, so you have a rational function f of x, and that is equal to 4x to the fourth all over x squared plus 8. Okay, and just taking what we have here. Okay, so for the denominator, again, this cannot be 0 in value. Okay, and again, if I try to isolate x squared, so I have x squared cannot be negative 8. And if I go from x squared to x, we'll have that x cannot be plus or minus the square root of negative 8. Okay, so you have plus or minus the square root of 8 times I, and technically those zeros can be reduced in terms of radicals. So you have plus or minus 2 times the square root of 2 times I. Okay, but again, we have this bit of history to repeat, so you have no real values are excluded. So once again, we'll have for the domain, we have the set of all real numbers. And in terms of vertical asymptotes, because there are no real values excluded, okay, we have no vertical asymptote. Then we'll have for 4x to the fourth over x squared plus 8. Okay, if we look at degree comparisons, okay, so I have n is equal to 4. And we have that m is equal to 2. And guess what? Looking at the comparison between n and m. Now n is greater than m, and there'll be a couple of consequences, okay, that can potentially arise, okay, just from the framework here. Okay, you have the n is greater than m by 1, or in this case, you have the n is greater than m by more than 1. And so we're not going to have any horizontal or slant asymptote. Okay, so already have no vertical asymptote. And guess what? I'm not going to have any horizontal or slant asymptote either. Okay, so just again what we have for this graph. Okay, now we have 4x to the fourth over x squared plus 8, and now it looks almost like a parabola. Okay, but we have with the extremes there's not going to be any asymptote. Now it looks as if you might be having, just on the basis of this graph, it looks like you might have vertical asymptote somewhere around negative and positive 3, but the thing about it is that it is expanding ever so slowly to the extreme left and extreme right, so it's kind of like going to the left toward infinity, and to the left to negative infinity, and to the right to positive infinity. And you have at the base, you have, looks like it's right at the x-axis, but for there to be a horizontal asymptote, you want a continuous part, you know, to be, okay, where you have running tangent, let's say to y is equal to 0, and you have only just this thin strip or thin section to where we have kind of tangent to y is equal to 0, but for that to be a legitimate horizontal asymptote, there must be continuity at either extreme, which we do not have, regarding this particular rational function. And now, just something to go ahead and be looking into. And tell you what, just for the next few minutes, let's see what we get for so we have determined the asymptotes as well as the domain. Now, say we have here looking for the domain and the asymptotes. Now, we'll say here we have r of x is equal to x squared plus 5. All over x plus 1. So for the next few moments, let's see what we get for the domain and the asymptotes of r of x is equal to x squared plus 5 all over x plus 1. Okay, if you're still working on the asymptotes, that's fine. But for what we have for r of x is equal to x squared plus 5 all over x plus 1. Okay, so we want to have, again, for the domain, okay, we cannot have a 0 denominator. Okay, so you have x plus 1 cannot be 0. So we want to have the x cannot be negative 1. And so we have with the domain, okay, we have those values of x less than negative 1, along with those values of x that will be greater than negative 1. Now for r of x, okay, now this is already in simplest form. So the excluded value, negative 1, that is going to be our vertical asymptote. Okay, now for this rational function, as we look into the degree comparisons, so we have in the numerator, so we have that n is equal to 2. And since we have x of first order, okay, we have m is equal to 1. So you're going to have that n is greater than m by 1 degree. So again, if there's a 1 degree difference where the numerator is higher in degree than the denominator, okay, so there's going to be a slant asymptote. So just looking at what we have with the polynomial division. Okay, so I have x plus 1 into x squared plus 5. Okay, if you notice, okay, we have a missing first order x term. Now, if you were to go with the long division route, okay, so again, we have x into x squared will go x times. X times x is x squared. X times 1 is x. And taking the difference. So we have x squared minus x squared, then we have 0 minus x. So we have negative x plus 5. And we have x into negative x go negative 1 times. And again, distributing, so you have negative 1 over x plus 1 is going to be negative x minus 1. And subtracting, so you have negative x plus x goes out. And we have 5 minus negative 1 will be 5 plus 1, so this will go to 6. So your quotient here is going to be at x minus 1. Now, since I have a linear divisor, you could have ended up going with the synthetic division. So I'll just mention this case. So if x plus 1 is equal to 0, I have x equal to negative 1. Again, from x squared, I have the coefficient at 1. And I'm missing a first order x term. So again, I would place 0. And again, the dividend closes out with a constant. So bring down 1. Negative 1 times 1 is negative 1. 0 plus negative 1 is negative 1. Negative 1 times negative 1 is positive 1. 5 plus 1 is 6. And again, so you had the remainder at 6. And for what we have in terms of the quotient, okay, the 1 here is in reference to x. And that's going to be x minus 1. So you have same quotient, same remainder. Okay. So for the slant asymptote, then we have the y is equal to the quotient, okay, which is going to be at x minus 1. So you have y is equal to x minus 1. Okay, and so just for what we have in the case of the illustration here, case we're in the graph. Okay, so we have x squared plus 5 all over x plus 1. Okay, so we have with the asymptotes. Okay, so I have x equal to negative 1. And if you notice this diagonal line here, this will be in reference to the slant asymptote, which we have at y is equal to x minus 1. And again, just the sections, the curves in the upper right and the lower left, we have in reference to y is equal to x squared plus 5 all over x plus 1. Okay, so again, you have two asymptotes, one vertical and the other one as a slant, or what some might call an oblique asymptote. All right, and just a quick item. And this being the case of, we're going to have in the next category, okay, this will be with polynomial inequalities. Okay, So you have like polynomial inequalities or inequality statements like less than, greater than, less than or equal to, greater than or equal to. And let's say that for polynomial inequalities. Okay, so just kind of get things kicked off here. Say we have first case, and we'll say that we have, we'll start out with a comparison to zero inequality. And say we have something like x squared minus 4 is greater than or equal to 0. Okay. So first of all, okay, to get to x squared minus 4, where it's going to be greater than or equal to 0, first of all, if we just take what we have as a comparison, going from a comparison to 0 to just equal to 0. Okay, so if I have x squared minus 4 is equal to 0, and we have in factoring, so I have x plus 2 times x minus 2 is equal to 0. And just looking at the factors, okay, so you have x plus 2 is equal to 0, x minus 2 is equal to 0. Okay, so we have starting out, okay, we have for your zeros. Okay, so we have negative and positive 2. Now, in terms of getting things set up, okay, so we have our numbers, our zeros at negative and positive 2. So what I'm going to do here, okay, so I'm going to set up a table. Okay, so we have an interval, and I'm going to work around negative and positive 2. Okay, so you have those values of x less than negative 2, okay, and bypassing negative 2, so we have those values greater than negative 2 and less than 2. And with 2 as the second and last is 0, we'll set up another open interval section. We have values of x that will be greater than 2. Now just provide some. Yes, I'm just going to separate these into rows and columns, and I'm just going to do this gradually. Okay. All right. So after setting up a table, now the headings will be just parentheses only. Okay. Okay, so you have working with the zeros. So you have less than negative 2, between negative and positive 2, and then we have greater than 2. Now, you're going to have, that's going to be a tested value for the input. Okay, so what that means is I can put in any value, say like for the first, okay, we have values of x less than negative 2. So as a tested value, okay, kind of like a probe, I can plug in something that is more negative than negative 2. And negative 3 would be a possibility. And say for test value x, something that is greater than -2 but less than 2. I might choose -1 or 0 or 1 if I want to go with integers. 0 would fit the bill. And we have for anything that is greater than 2. Okay, we can just go like 3, 10. Let's see. We'll just go with 3 on this one. Now, in terms of what I'm going to do with these numbers, okay, now, we started out, okay, we have compared to 0, we have x squared minus 4. Okay, so we have for f of x equal to x squared minus 4. Okay, so we have f of -3, and if I plug in -3 for x, and you just put in the number. So the square of -3 is going to be a positive 9. We have minus 4, so 9 minus 4 is equal to 5. And I'm going to place emphasis upon the sign value. Okay, so the difference here is going to be a positive 5. Now with x at 0, okay, so we'll have 0 squared. We have minus 4. 0 squared is going to be 0. And 0 minus 4. Okay, so that is going to be a -4. And for what we have in the case of f of 3, okay, so we'll have 3 squared minus 4. 3 squared is 9. And 9 minus 4, okay, so that is going to result as a positive 5. So just going back to the table we have. What I'll do here, just kind of provide a little bit of room in terms of adding any rows. Okay, and so for what we're going to have next, and for this remaining row, okay, so we're going to have for the sign of f of x. You notice, okay, whenever I use -3 to represent anything less than -2 for the input, the output resulted as a positive value. So anything I plug in that is less than -2, the output is always going to be positive. So if the output is positive, this would mean that f of x is greater than 0. Now, having tested out 0, if I plug in anything that is greater than -2 but less than 2, had I chosen like maybe -1.9 or 0.79, the output is going to be a negative. If you have a negative value, that means that your function value is going to be less than 0. And then anything greater than 2, whether it's 2.5 or 3 or 17, the output is always going to be positive. So here we're going to have that f of x is going to be greater than 0. Now, I'm just going to kind of cap things off, okay, just with a little bit of a composite summary. Okay, if you notice, we have at the end, okay, we have comparison to 0 statements. and I'll just show you like the other ways that the problem could have been presented. Okay, let's say that, okay, for x squared minus 4 is less than 0. Okay. What this is going to be referencing is going to be where we have f of x is less than 0. Okay. And guess what? So I already have your f of x is at x squared minus 4. And where x squared minus 4 is less than 0, you're referencing where f of x is less than 0. Now for your solution, okay, so where f of x is less than 0, you're looking at the interval section in the top row, and guess what? Where f of x is less than 0, we have between negative and positive 2. Now, if the statement had been x squared minus 4 is less than or equal to 0, okay, and I was going to mention, okay, so this would be where f of x is going to be less than or equal to 0. I'm using a little bit of color coding since I had the zeros from the top before setting up the table. Now, in the case of your solution, okay, notice, okay, we have less than or equal to 0, so it's going in the same direction as less than 0. Now your limits, you do have involving negative and positive 2. But now with the equal sign, we're going to be inclusive of both negative and positive 2. Okay, so you had just kind of like from the start here, thanks to the equal sign, your solution is going to be brackets around negative and positive 2. Now say now for x squared minus 4 is greater than 0, okay, so you have f of x is greater than 0. Okay, so if you're less than, greater than statements, it can reference the corresponding top rows for the solution. And guess what? Where f of x is greater than 0, so you're looking at the first as well as the third interval section. So you have in your solution where it's greater than 0, so you have from negative infinity approaching but not including negative 2, and tied in, okay, so you have in union with values of x that will be greater than 2. And now, just for the problem itself, okay, so for x squared minus 4 is greater than or equal to 0. Again, direction-wise, it's going to be the same as f of x is greater than 0. But again, you're going to have your values that make this expression equal to 0 also included. Alright, so I kind of worked 4 problems in one, but for this one specifically, and we have for the solution, okay, so for the greater than portion, so we're still involving negative infinity and negative 2. And we're still involving 2 and infinity. And in terms of the closing out, what we have here. Okay. Now again, infinities are boundless. So we're going to have parentheses around the infinities. But now, okay, now for the greater than side, okay, again, we have parentheses around negative and positive 2. But now, with the statement inclusive of the equal sign, we have negative 2 and 2. Make this polynomial equal to 0. So, in this case, we will have around negative and positive 2. We'll end up with a bracket. Okay, so just as a comparison to zero inequality, these are your 4 possible cases. All right, so if you have less than 0, this is your interval solution. Less than or equal to, you got the same numbers, but you got different grouping symbols, where we have negative and positive 2 are included. And for greater than 0, again, you have values less than negative 2 as well as greater than 2. And then we have for greater than or equal to 0, again, negative and positive 2 are included as indicated by the brackets. Okay,